This section explains why the review chapter on basic set theory comes first, and what it is quietly stocking for everything that follows. Before a program can be given meaning, you need a language to give meaning in, and that language must sit one level above the programs it describes. That is the whole point of this review chapter. It stocks the meta-language, the ordinary mathematical prose of sets, membership, relations, functions, and the quantifiers there exists, and functions and the quantifiers. There exists and for all, in which every later semantics will be written. Winskell flags the separation explicitly. This notation, he cautions, is not to be confused with the formal languages of programming languages we will encounter later. The object being studied and the tool doing the studying are different strata. Conflating them is the beginner's error. The chapter preempts. Conflating them is the beginner's error. This section explains why every account of a program's meaning needs a language to be written in, and what that language is. Every account of what a program means must itself be written in some language, and that language cannot be the programming language it describes, or the account circles back on itself. This chapter fixes the meta-language, informal set theory, and logic, the vocabulary in which all the later semantics gets stated. Sets, relations, functions, quantifiers are not yet objects of study here. They are the medium of study. The one move that carries the whole book is the partition between the language you reason in and the language you reason about. Winskell flags it at once, warning that this notation is not to be confused with the formal languages still to come. Master the vocabulary, and every later construction is just this same vocabulary, turned on programs. This section introduces how operational semantics gives a program its meaning by making it run. Meaning comes from running. IMP's semantics does not map the program into abstract values. It is a set of inference rules stating how a configuration, a command paired with a state, steps to a final state. The rules sit so close to an implementation that Prolog reads them almost directly. The move that makes this work is that one rule attaches to each formation rule of the grammar. So meaning is defined by recursion on syntactic structure. This is Winskell's structural operational semantics. A program is what its rules make it do to the store. Because meaning is a derivation, command equivalence becomes provable. Two commands are equal when they force identical state transitions. The pattern generalizes. Give any construct meaning by giving its transition rule. This section explains how operational semantics gives meaning to a program. Meaning is a relation. Define the way a set is inductively by syntax-directed rules. A configuration pairs a syntax fragment with a state. The fragment are written together with the state sigma inside angle brackets. Each rule fixes how the whole evaluates from how its parts do, with premises written above the line and the conclusion below. To run a program is defined as this: search upward for a derivation tree that bottoms out in axioms. It is one move everywhere. Arithmetic, Boolean, and command each get their own such relation, each built from the relations of its subterms. It is an inductive definition wearing the costume of natural deduction. Meaning as relation then buys command equivalence for free. Two commands are equal if and only if they induce the same state map. The rules double as an interpreter, and that is precisely what makes the semantics operational. This section explains why every induction you have met is a single principle in disguise. Every induction you know is one move wearing different clothes. Mathematical induction, course of values, induction, structural induction, each proves that P holds everywhere by proving it holds at an element whenever it holds, at an element whenever it holds at all of that element's predecessors. What makes the move valid is a single property of the predecessor relation, not the natural numbers and not the syntax tree. That property is this: no infinite descending chain. Take successor, take strict less than, take immediate subexpression, take any well-founded relation at all, and the principle specializes to a named induction for free. Here is the generative kernel. A non-empty set of counterexamples would need a minimal offender. Yet minimality together with the induction step forbids that offender from existing. Well-foundedness is the whole engine, and the familiar inductions are its instances. This is Emmy Noether's principle, hiding under three names. This section explains why one proof engine underlies all the others. Mathematical induction, where the natural numbers are built by successor, and structural induction, where expressions are built by constructors, are not two techniques. They are one technique, well-founded induction, specialized to two relations. A relation supports induction exactly when it admits no infinite descending chain. Equivalently, every non-empty subset has a minimal element. That equivalence is the whole content. To prove that a property P holds everywhere, it suffices that P cannot first fail. No minimal counterexample survives. Winskell builds this so that every later claim in IMP, every claim of the form for all programs, runs on the same wheel. Determinism of evaluation is its first turn. Now predict the rest. Any constructor-built syntax carries its own subterm order, and hence carries its own induction. This section explains what it means to build a set from rules, and why one proof principle falls out of that construction for free. A set built from rules is not a list of what you put in. It is the smallest set closed under those rules, admitting nothing a derivation cannot reach. That minimality is the whole content. Everything in it has a finite derivation, and nothing else gets in. Induction is the shadow of leastness. Because the set is the least closed one, any property closed under the same rules already contains it. So proving that the property survives each rule, from premises to conclusion, proves it of the entire set. Rule induction is exactly this move. Syntax, evaluation, and execution are all instances, and structural induction is the special case. This is the chapter's work in the book installed the one principle that every later proof about the semantics of IMP will invoke. This section explains what an inductively defined set really is, and why its minimality carries the whole of Winskell's Chapter 4. An inductively defined set is not a list of what you put in. It is the smallest set already closed under its own rules, containing nothing a derivation cannot reach. That minimality is the entire content of the chapter, and it is generative. Because the set is least, any property preserved by every rule, true of a rule's conclusion whenever it is true of a rule's conclusion, whenever it is true of a rule's conclusion, whenever it is true of the premises, is automatically tree and not reach. That is rule induction. Structural induction on expressions and the proofs about IMP's evaluation relations are its special cases. Winskell collapses them all into one move. The dual reading, least closed set below and induction principle above, is Chapter 4's single primitive, seeding every semantic argument the book will make. This section explains how the denotational semantics of IMP relocates a program's meaning from its motion to a function. Operational semantics defines meaning by how a program moves, step by step, with syntax tangled into every rule. The pivot is this. Two commands are already indistinguishable, exactly when they compute the same partial function on states. C0 is equivalent to C1 precisely when both determine the same set of pairs, an input state sigma together with the output state, sigma prime. A command's denotation, written C of C, is a partial function from the set of states, sigma to sigma. It is the object the syntax merely points at, and the brackets quote the syntax so that you do not evaluate it. This function is built by structural induction, the meaning of the whole assembled from the meanings of the parts, never from execution traces. This is the quotient. Then name, move. First you collapse commands by observable equivalence, then you christen the equivalence class, the thing itself. This section explains what a program means once you strip away how it runs. A program is the partial function on states that it computes. Nothing about how it runs survives the abstraction. Strip the syntax, keep the input-output map, and two commands are equal exactly when they denote the same function. Equivalence stops being a theorem about matching transition steps and collapses into plain function equality. Each construct's meaning is assembled from its parts' meanings, a homomorphism from syntax to denotation, built by structural induction. The chapter turns on the single place that recipe fails. The while loop denotes itself, phi equals r of phi, admitting no direct definition. Its meaning is instead the least fixed point of the unfolding operator by Nastor and Tarski. Meaning as the solution to an equation, not a construction. This section explains how the axiomatic semantics of IMP fixes the meaning of a program through provability. Meaning is defined by provability rather than by tracing execution. Instead of following a program state by state, you fix what a construct means by the rules for proving properties of it. A command C is characterized by which precondition and postcondition pairs it validates. Written as a triple, a precondition, A, the command C, and a postcondition, B, it reads every terminating run from a state satisfying A lands in one satisfying B. This buys the leap that running cannot make. A single proof covers the infinite family of initial states, Winskell's arbitrary P, that no execution could ever enumerate. The cost hides in the name. Partial correctness says nothing when C diverges, so the triple with precondition true, command while true do skip, and postcondition false holds vacuously. A program becomes what you can prove about it. This section explains what changes when meaning becomes something you can prove rather than something you run. Meaning stops being what the program computes and becomes what you can prove about it. A command C is pinned by a triple, A, then C, then B, start in a state satisfying A, terminate, and end in a state satisfying B. The state the command produces is no longer the anchor. Each construct earns an inference rule, and those rules are its semantics. That is why the approach is called axiomatic. The catch that does the real work is the word partial. Saying nothing about non-termination makes a strange triple valid true. Then while true, do, skip, then false. A diverging computation satisfies every postcondition. Structurally, this is the same move Winskell has run since Chapter 5. An object is what it does, but does now means what it licenses you to conclude, where before it meant what the command runs to. The chapter builds the proof calculus. Chapter 7 asks whether it proves enough. This section explains what completeness means for the Hoare rules and why it can only ever be a relative claim. Soundness, said the Hoare rules, never lie. Completeness is the converse claim that they never miss. Every partial correctness assertion that is semantically true is formally derivable, so the syntactic proof system and the semantic truth relation coincide exactly. The surprise is that this cannot hold outright. Derivability of the assertions themselves is undecidable, so completeness is only relative. Granted an oracle for valid assertions, the program logic rules add no further incompleteness of their own. The whole reduction turns on one hinge. The assertion language must express the weakest precondition of every command. Completeness is thereby smuggled into expressiveness. The logic is complete precisely when it can name what each command demands of its input. This section explains why completeness fails for this chapter's proof system, and why that failure says nothing bad about the program logic itself. Completeness fails here, but not because the program logic is weak. It fails because the system-inherited girdle, no effective proof system, captures exactly the valid arithmetic assertions, and the rule of consequence leans on precisely that judgment. The chapter's move is to factor the failure. Grant an oracle that answers which assertions are valid, quotient that inherited limit out, then ask whether the program reasoning machinery alone is complete relative to it. Cook's answer is yes. Every valid triple, an assertion A, a command C, and an assertion B, is provable modulo arithmetic, truth. So the chapter's job in the book's arc is to certify that Hoare logic loses nothing of its own. All the incompleteness lives in the assertion language, none of it in the rules for the constructs. This section introduces the core idea of domain theory. Order the possible meanings by how defined they are, so that more information sits higher and every question about computation turns into a question about limits. A domain is a set of denotations carrying just enough order that ascending chains of partial information always have a least upper bound. A computable map is continuous, which means it commits to nothing at the limit that it had not already committed to somewhere along the way. Recursion is the one construct that resists naive definition, and it resolves as the least fixed point. You feed ignorance, written bottom, back through the map again and again, and take the bottom-up limit, the least upper bound over n of the map applied n times to bottom. The is-once dream detector is the whole thesis in miniature. It places a don't-know value, bottom, below true and false, with the output information tracking the input information monotonically. Denotational semantics is just this, discipline carried out in full. This part explains why continuity is the only law a computable map can obey. A meaning is a point in an ordered space where higher means more defined. The only maps allowed are those that never wait for the whole infinite input. They commit on finite evidence, then pass to the limit. That constraint is continuity. The value on an infinite object is nothing but the accumulation of values on its finite approximations. Windscale's isonion streams in Chapter 8 shows why nothing weaker survives. A detector that would revise false to true once a late one arrives is not a function on the domain at all. Recursion then solves itself. Iterate a continuous map starting from bottom, and the climbing chain's least upper bound is the least fixed point. This section explains what a recursive equation actually specifies. A recursive equation, like f of x equals f of x plus 1, constrains a function rather than defining one. Many functions satisfy the constraint, so its meaning is the least of them. the fixed point that commits to divergence wherever the equation forces no answer. This is the while loop's least fixed point selection, imported wholesale, now applied to functions rather than commands. The genuine surprise is that the equation still underdetermines. Whether a divergent argument bound to an unused parameter poisons the enclosing call is not fixed by the text. Call by value evaluates arguments first and propagates that divergence. Call by name passes them unevaluated and discards it. The evaluation strategy is what selects which least fixed point the one equation denotes. This part explains what a recursive equation really is. A recursive equation like f1 of x equals f1 of x plus 1 is best read as a constraint rather than a definition. Taken as a fixed point condition that the function environment must satisfy, it admits many solutions, or none. Meaning is fixed as the least of them. The fix of one of x equals environment must satisfy. This is the same move the while loop already forced, now lifted from state transformers up to functions on the integers. Recursion is also where a second axis first becomes visible. You can evaluate arguments before passing them, which is call by value, or pass them raw, which is call by name. That choice is not cosmetic. The expression phi u of f1 of 3 diverges under one reading and terminates with the value 1 under the other. The chapter's labor is showing that the operational and the denotational readings of each coincide. This part explains why recursion needs a proof toolkit at all and what each technique in the chapter buys you. A recursive definition denotes a least fixed point, but you cannot reason about it by running it to completion because the unfolding never terminates. Every technique here converts a claim about that infinite object into one you can prove without ever unfolding it. Park induction is the seed. The fixed point of f is the least prefixed point, so to bound it from above, you need only exhibit some d, for which f applied to d is less than or equal to d. A single inequality stands in for the limit. The rest of the toolkit widens that move. Becky rewrites simultaneous recursion as nested one-variable recursion. Scott's fixed point induction climbs the chain of finite approximants for any inclusive property. Well-founded recursion licenses definition by descent. The chapter is the proof toolkit that makes the fixed point denotation of chapters 5 through 9 actually usable. This pod explains how the 10th body reasons about an object built as an infinite limit without ever running the limit to completion. The whole chapter is a single problem. An object is defined as the least fixed point, the least upper bound over n of f applied n times to bottom, and the task is to reason about it without ever performing that limit. The one characterization that makes this possible is the least prefixed point. If f of d is below or equal to d, then the fixed point of f is below or equal to d. This single property lets every technique trade induction over n for a closure condition on the property itself. You prove the property at bottom, you prove the property at bottom. You prove the property at bottom, you prove that f priest point. That is Scott's fixed point induction, and it never counts to infinity. The price is inclusiveness. Only predicates that are stable under the least upper bound survive the passage from the approximants to their limit. A property that holds at every finite stage but breaks in the limit is not admissible, and the method cannot use it. Becky is the same move, made sideways. A simultaneous recursion is just nested one-coordinate fixed points, the same kind of object seen along another axis, so it needs no new machinery. The whole shape of the chapter reduces to one sentence. Techniques for recursion are techniques for not iterating. This layer explains what a single constructor does. Close the type grammar under a function space, the arrow that builds function types, and functions stop being second-class fixtures. They become values. You can store them in pairs, pass them as arguments, return them as results on equal footing with the integers. That single closure is what separates REC's first-order recursion, the subject of Chapter 9, from a real functional language. The eager reading collapses to standard ML, the lazy one collapses to Haskell. The same call by value versus call by name fork you already met recurs at every arrow. Everything downstream is forced by this one move. Fixed point operators, adequacy, the failure of full abstraction. The denotational domain must now hold functions as inhabitants, so it can contain more than any term can name. This section explains what a single new type constructor does to a whole language. Add one constructor, the function space from tau1 to tau2, and the language turns on itself. Functions stop being how you compute values and become values themselves. So the space of meanings must be closed under the very operation the semantics interprets. That reflexive closure is the whole chapter. It forces the fork. The imperative language is never faced. Eager versus lazy, call by value versus call by name. The reason is that when an argument is evaluated, is now observable in what a function returns. And it reopens the match between denotation and execution. Does the mathematical meaning see exactly what running the program sees? Adequacy and then full abstraction are the names for that question, once values can themselves be functions. This section explains the idea behind information systems. Stop describing a domain by its points. Describe instead the finite assertions one could truthfully make about a computation related by consistency and entailment. The domain returns for free. Its elements are exactly the consistent, entailment-closed token sets ordered by inclusion, each infinite point the union of its finite approximations. That is the inversion the rest depends on. Replace an object by the logic of what is observably true of it, and the object becomes syntax. Syntax admits inductive definition, hence recursion. So recursive domain equations, the ones written as x is isomorphic to f of x, are the ones inductive sets cannot reach, strings, and Scott's equation, d, is isomorphic to the space of continuous functions from d to d. These collapse to the least fixed point of a continuous map over information systems ordered by substructure. This part explains why you should describe a notation for a domain rather than the domain itself. A domain is hard to define recursively because its infinite elements resist induction. So stop describing the domain and describe instead a finite notation for it. Tokens, which are assertions about a computation, closed under consistency and entailment. The Scott domain then reappears for free. It is exactly the consistent, entailment-closed token sets ordered by inclusion, its infinite elements assembled from finite approximations. The payoff is the whole chapter. Because information systems traffic only in finite data, they submit to inductive definition. So the space of systems is itself a SIPO. And solving a recursive domain equation where x is isomorphic to f of x collapses back into taking a least fixed point of a continuous operator, machinery already in hand. Move the recursion from objects to their descriptions. This section explains recursive types as fixed points. A recursive type is a fixed point. Write it as mu x dot tau. This solves the type equation that says X is isomorphic to tau of X, the type that equals its own unfolding. The chapters move, extending. Chapter 11's eager and lazy languages is to refuse the conflation. The type mu x dot tau and its unfolding tau with mu x dot tau substituted for X are isomorphic. The isomorphism is explicit, so the two are related by a pair of coercions and never silently treated as one and the same type. The constructors abs and rep are the two coercions and never silently treated as one and the same type. Every recursive datum then carries its own fold and unfold witness. 0 is abs applied to the left injection of the empty tuple. Suck is abs applied to the right injection of its argument. Semantically, the fixed point is real. Systems denote these types because they admit the least solution of the equation, and that concreteness is precisely what buys the simple adequacy proofs. This section explains what a recursive type is at the structural level. A recursive type is a fixed point of a type equation, the same move that recf performs on functions, lifted one level up to types. Write x equals tau of x. Then mu x dot tau names its solution, the naturals, as mu x dot 1 plus x. Lists as mu x dot 1 plus x. Lists as mu x dot 1 plus n times y. Even a model of the untyped lambda calculus as mu z dot, the function space from z to z. The isomorphism between mu x dot tau and tau with mu x dot tau substituted for x is the entire content. Abs and rep are merely its two directions, fold into the type and unfold back out. Once you can name that one isomorphism, every constructor and every case analysis on numbers or lists is derived. This section explains why parallelism forces non-determinism into a language's semantics. Parallelism is non-determinism, wearing a mechanism. The chapter turns on a single move. Once two commands run together, say the assignment x becomes 0, in parallel with x becomes 1, you can no longer model a command as a function from a command as a function from a configuration to a final state, because a step of one command mutates the state. The other is about to read. So the semantics is forced down to single, uninterruptible steps, and the outcome becomes a relation rather than a function. Which interleaving actually occurred is exactly the information the relation refuses to fix. That refusal is non-determinism. Everything downstream rests on this one concession. Dijkstra's guarded commands CSP, CCS, and the modal logic that checks a process against a specification are all built on it, to compose in parallel, forget which order won. This section explains why parallel composition forces a new foundation for the whole chapter. Parallel composition breaks the one assumption every prior chapter rested on, that a command is a relation from initial state to final state. Once two commands share a variable, each can rewrite what the other is about to read, so the endpoints no longer determine the computation. The interleaving does. The fix forces the whole chapter. You abandon the big step, input to output relation for a small step transition. Relation whose single atomic moves expose the state between the steps. Non-determinism is simply that structure seen from outside. Forget which interleaving ran, and one program yields many outcomes. Everything after this, guarded commands, CSP, CS, and a modal logic to specify processes, is climbing the ladder. This one move opens.